flux core arc welding. Now this is a process that I don't do quite as much of as I'd like to, but that being said, it's still a really popular process and it's something that a lot of people have requested that I make a video about, so that's what we're going to be doing. The purpose of this video is just to act as an introduction for someone who has little to no experience in flux core arc welding, and hopefully it'll give you everything you need to get off and running on the right foot in your welding adventures. So with that being said, let's check out the wire we're going to be using. So this is some Lincoln Electric NR211 type wire, and I picked this up from a local big box store. Don't exactly remember which one because I've actually had it for a couple weeks, but I already got it unboxed. Came in a nice plastic baggie to keep all the moisture out. I removed that. I actually ran some of this prior to shooting this video just so I'd be a little bit practiced up for you guys. Now one thing I'll put out there is if this is the wire that you decide you want to use, which I think it's really good wire just for general purpose, you know, self-shielded flux core applications, is that both Lowe's and Home Depot sell this stuff, and they both price match each other, so you can usually just figure out which store has it cheaper, print that off, print that off the internet, take it to the other store, and they'll match that price plus like 10% or something. I don't know how useful that's going to be for you, but when I started welding, I was pretty much broke, so those few bucks really would have made a difference. But anyway, this is the wire we're going to be running. Now we've got some solid MIG wire in there now, which we need to remove, so I'll just go ahead and twist off that nozzle. Depending on what type of welder you're using, it might be that same exact system or it might be something completely different. Then I'll just go ahead and remove the contact tip. Now it should go without saying, but may or may not, depending on how much you know about this. You want to be careful that these size contact tip you're running is comparable to the size wire you've bought, so that's something that's good to check up on. If you're not sure if your tip is all nasty and messy and you can't really read it, it's probably a good idea to just put another one in there anyway. You know, they're pretty cheap and they're something you'll want to keep on hand, as I'm sure you already know. Alright, now with that removed, I can just feed the wire back through the machine. I just turned that spool there until the last of the wire came out. I wrapped the end of the wire through the hole in the spool, and now we're going to do the reverse of that. I just went ahead and installed my spool of flux core wire. I'll cut off the end there that was bent because obviously the bent end isn't going to want to go through the liner. And with the contact tip and everything off and out of the way, I'll just pull the trigger and wait for it to run through, and then I'll just reassemble the torch to the opposite of how we took it apart moments ago. Now this here is some of the safety gear we're going to be using. I always tell folks that, you know, self-shielded flux core wire generally has a lot of the same safety requirements as does shielded metal arc welding or stick welding, and I usually just carry the safety equipment right over from that process to this one. I recommend using a full set of welding leathers because this is pretty bright and there is a lot of spatter, so you know it's definitely not something you want to do in a t-shirt, and some stick welding gloves. However, for really light duty work, you would probably be fine just wearing a good cotton welding jacket and some MIG gloves, but again, I recommend going all out and wearing the stick apparel just in the name of safety. Now you're also going to need a few other things. I got my slag chip and hammer here because this is of course the process that produces slag, unlike say MIG or TIG welding, as I'm sure you know. I got my welder's pliers here just because those are going to come in handy for the wire feed aspects of setting up the machine and everything. I got a wire brush to help with the cleaning, and I got the safety glasses. These are very important because obviously we're going to be chipping slag like I just mentioned, and also if you do flash yourself, this will work to lessen the chances of getting arc eye, and just safety glasses are of course a good thing to wear in any welding, work type environment. Now something else to keep in mind is this is a very smoky process as well. If you're not getting the picture yet, it's sort of a somewhat messy process, if you will. And so because of that, good ventilation is very, very important. If you can use a fume extractor like this, I'm going to say that's probably your best option. If you don't have a fume extractor, some good large fans and natural ventilation, or if you're in a place where you can do it safely without starting a forest fire, welding outside is another option, which might be a good thing. And this isn't going to be some super in-depth technical deal. I just want to get you guys started on doing some flux core arc welding, if you got the machine and if that's something you want to do. So we got the voltage and we got the wire feed speed here. Now the way I think of this is voltage is how much power we're going to be using to weld with, and wire feed speed is how much filler metal we're adding to the weld as we weld. So think of your voltage kind of like your heat, and your wire feed speed is kind of like the amount of metal that's going in. And in order to make a proper weld, you're going to need to balance these things out, and you don't want to run too much voltage compared to the amount of wire feed speed that you're using. You also don't want to do the opposite of that, of course. And so first off, I'm just going to show you guys this. This is what I'd consider to be a properly done flux core weld. But listen to what this sounds like and just watch what it looks like. Now I'm going to be giving you all some pointers on how to set up a machine here. You know, that's assuming that you don't have like a door chart or something that you can start with on your machine. It'll tell you, you know, put the voltage to letter A if it's set up like that, and wire feed speed to like 6 out of 10 or something. If you don't have that, hopefully this will sort of get you going in the right direction. If you do have that, this could still be useful just in terms of fine-tuning things. But this is the finished weld. As you can see, it lays in there flat. There's no undercut. Undercut's just like a deep gouge. It goes into the top plate. It ties in pretty well. This is what's going to happen if you're not running nearly enough voltage. So essentially what we're doing here is we're adding too much metal and not enough heat. The amount of heat we're using isn't enough to adequately melt the amount of metal that we're working with, and as you can see, it's just really sputtery because there just isn't enough heat to process this, so all the metal's just sitting there essentially on top of the weld. That was an extreme case. This is not quite as extreme case here. Now we're running 20 volts instead of the 25 that I'd been running so far, and as you can see, it is kind of welding, but it's still really sputtery. It's not smooth at all, and this right here is the finished product. Yeah, as you can see, I'm doing some slag chipping action here. Not entirely sure why. Don't really know if I thought I was going to make this look all that much better. But yeah, this is what we got. This is the extreme cold case. As you can see, we just don't have enough heat to melt the metal, so the metal just piles up and makes that big old mess. This is the just another shot of that. As you can see, there's a huge ridge between the weld and the metal, so we know that's not fused in there well. This would not be a strong weld. It would not be what I don't think anyone would consider to be an acceptable weld. This is the not quite as extreme case. As you can see, instead of laying in there flat, it's pretty convex. It still has those sharp ridges. And this here is the opposite problem. This is what happens when you don't run enough wire feed speed for the amount of voltage you're using. As you can see, the arc is huge, and because of that, you know, the arc is really powerful and there's not enough metal for it to burn, so it's just kind of overburning, I guess you could say. It's really indirect. It's just slinging metal everywhere. It's making a big old mess. It's not pretty at all. And this is what we got here. As you can see, there's a lot of undercut here. We got that deep gouge like melted into our base metal, and you know, that's definitely not something that you want to have either. So, you know, generally, if using this criteria you determine that you're running too much wire feed speed, you have two options. You can turn down the wire feed speed to match the voltage, or you can turn up the voltage to match your wire feed speed. If you're working with thinner material, you might want to turn the welder up. If you're working with thicker material, you might want to turn it down, but you know, it could be the opposite of that as well. You're pretty much just going to have to practice with this and use your best judgment. So now let's talk about work angle and travel angle. So alright, first off is going to be, I guess, work angle, I think is what I'm demonstrating here. Now as you can see right now, I got the gun sort of pointed into the middle of the joint, and that, you know, would be okay. Now if I angle it like this, all our metal that we're putting down is going to end up on that bottom plate with very, very little, if anything, fusing into the top plate, and that's not good. Now here, if I angle it like this, you know, I'm going to have the opposite problem. All our metal is just going to stick to that top plate. We're hardly going to tie into the bottom plate at all. So what I want to do is just angle myself into the plate, you know, at a 45-degree angle, then move the gun down a little bit like you'll just saw me do. And this way we're kind of stacking the metal upwards some, and gravity is going to come into play and pull that down. So hopefully if we do our part right, then we're going to end up with a weld that's evenly distributed between the top and the bottom plates of our joint. Now let's talk about drag angle. You don't really want to push self-shielded flux core wire because, you know, if you do, all that slag goes in front of you and you end up running it over, and then you can have slag entrapment. So I just like to use a slight drag angle just like that. Nothing too big. If I'm going in 90 degrees, I just angle the gun back a little bit just like that and weld away. Alright, now let's talk about travel speed. You know, even if you get everything set up perfectly and you're doing your part and everything's going right, if you're not traveling at the right speed, you're still going to get a bad weld. Pretty much anything can sort of work to screw you when you're welding it if you don't really know what's going on. So this is just a demonstration of what happens when you travel too slow. As you can see, I've got a monstrous weld bead here. It's way too big for the weld metal, and we're just dumping heat into this weld mat. Actually, I just burned through there, and I think I'm about to burn through here again. And I mean, we're getting this overheated. We got a weld that's excessively huge and just everywhere and nasty. We burned through two different places. and that's definitely not good. So you'll know if you're traveling too slow, if your weld is getting too big for the workpiece that you're working on, and you know, if things start to overheat, you know, you might want to speed it up just a little bit. The other thing is, if you pile on too much metal, it's not going to be able to adequately fuse because you're not putting the metal where it needs to go. You're putting the metal on top of where there's other metal, and like I said, it's just going to pile up and be a mess. Now this is the opposite problem. This is traveling too fast. Now if you travel too fast, essentially what's going to happen is the arc isn't going to have enough time to put the heat into the puddle to properly fuse into the metal, and you just end up with this stringy mess here. And also because you're moving so fast, you know, the most obvious problem is you're just not staying there long enough to put down the amount of metal that you need. And this is a small weld. It obviously looks really bad. I'm sure this isn't going to be strong at all. I mean, it's probably isn't going to hold a whole lot more than its own weight. It's just, yeah, it's just really narrow, really stringy, really big mess. Now this, for comparison, is what I consider to be a proper travel speed. Yeah, as you can see, we're just working along. We're not overheating our plate any. We don't have undercut. We don't have material just piled up on top of itself, which is commonly referred to as cold lap. We just have this nice flux core, kind of, I guess you could say, almost crinkled appearance. All right, anyway, let's, I guess we might as well just weld out a few more joints here. As you can see, I'm doing some outside corner joints. This is pretty much the same thing, you know, we just get our welder set so we don't have the, you know, too much voltage or too much wire feed speed problems that we demonstrated earlier. And once we got the travel speed figured down, we pretty much just work our way across the joint. And this is what we're left with. From this point on in the video, I didn't really bother to leave in the slag chipping scenes because I figure people probably only want to watch so much of that. But anyway, this is the finished outside corner weld. As you can see, we don't have any undercut. It's just laying in there real nice. I mean, that would hold a lot of weight right there. Next thing we're going to be doing is a lap joint. This is, as I'm sure you know, just where two pieces of material meet with each other. You know, one overlaps the other, and you just kind of weld where they overlap. And so we're just working away here. The other thing is, you know, once you get your machine dialed in for the rough thickness of material that you're working with, you can do a lot with it, a whole lot of different joint configurations once you have a general understanding and feel for how things are going. And flux core welding isn't a process that I use a whole lot, but now I got most of a spool left over here, so that might be subject to change coming soon. I don't know if y'all would like to watch some more flux core arc welding videos, but anyway, yeah, we're just welding away, having a grand old time here, and we're going to have our lap joint done in a second. I'm just dragging the puddle along. As you can see, I don't want to be running over any slag. I don't want to have issues with slag entrapment, porosity, or anything along those lines. And this is what we're left with. As you can see, the weld just lays in there real nice and flat. Yeah, it's just, I'd consider that to be a pretty decent lap joint. Unfortunately, like I said, don't expect TIG stack of dimes level appearances on these welds, but you can get some pretty decent looking welds when it's all said and done. But alright, well, hopefully this video is what you need to, like I said, get yourself off on the right foot, get yourself off to a good start with your flux cored arc welding adventures. As always, just remember, safety first, take your time, be careful, and yeah, thanks for watching, everybody. Don't forget to rate, comment, and subscribe for more.